Alright, APCalc class, we're going to take a look at section 4.1, and this is going to be working with antiderivatives and more so the analytical side of it. We've already studied the limit definition of the integration, and we've also done the Riemann sums and studying the area, with different left hand, right hand, midpoint rectangles, trapezoidal. But now we're gonna concentrate more on the analytical or algebraic way or formula method of finding these antiderivatives or integrals. Okay, so let's just ask yourself, if we want to define, they call it capital F of x, whose derivative is given as lowercase f of x equals 3x squared. Okay, so this is usually the notation. So if they're giving you this function, meaning that this was the derivative of some function, and then you want to go backwards instead of, when we have f and we want to find its derivative, we call it f prime. But if they give you f of x and they say, hey, I want to find the antiderivative, they usually go with a capital F of x. So you might be able to just kind of think backwards on this, because you know that the rule for finding derivatives is that simple power rule. So maybe you can come up with, well, I'd have to have x cubed, so that when I multiply the exponent down and take one away, I would have 3x squared. But it says, there's actually many, because we could have any constant being added or subtracted after that x. The important part is that we get x cubed, because that's going to give us that 3x squared. But we could have had a +1 or a -7 or a +38. It doesn't really matter. But if we have some constant here at the end, that would disappear after we do the derivative. So when we do take the integral or the antiderivative of a function, we always want to follow it with a +c. Now that just means it could be any constant that was added, whether it's positive or negative number, but we could have any constant added on at the end. All right. Okay, so talking about the notation, instead of writing what function would we have the derivative of, we write, we've already used this symbol, the we've called it an integral, right? The integration, we talked about it geometrically with being the area under the curve, but it's read the integral of f of x with respect to x. So generally we say the integral of f of x with respect to x, so that's the dx, would be equal to, and then like I said up here, they use that capital f of x plus c. So after you take the antiderivative of f of x, the general notation is they use the capital F of x plus c. Okay, so it says the integral looks like an S. That's not accidental, because we're going to talk about that, because we've already discussed the sum of the the rectangles, right? So for sum, it says you must always write a plus c after your integral's answer, and that's kind of demonstrated here. Okay, so a lot of these rules, these first 5, they follow what we've already talked about. If we have multiple functions being added, you can integrate each piece separately, whether you're adding them or subtracting them. If there is a constant multiplier, or let's just say for rule number 2, if it was just a constant. So if I were taking, let's say, the antiderivative of just 3 or something like that, right? And if it had we always put dx, that means with respect to x, or it's your variable of integration. Okay, so when I would take the antiderivative of that, I would just tack the x on there, right? Because if I take, and then think about your answer, if I take the derivative of 3x, that would just equal 3 then, right? But I always put that plus c at the end, okay? And then the other thing is, if you have a constant multiplied in front of your function, that can get pulled out. We did that quite a bit when we were introducing the integrals by geometric means. We saw that we can pull that out. We talked about these ones. This rule number 6 is kind of the big main rule. It's kind of like our power rule for doing derivatives. There's a power rule for integration as well. And if you recall, with derivatives, we multiply and then subtract from the exponent. So if we're doing an inverse operation, an integral, which is the inverse operation of derivatives, then we do those operations in reverse. So what we do is we add 1 to our exponent, and then we divide by whatever that n plus 1 was, and add your plus c. So here's what I mean. So for part A, maybe what we do first is we pull this 3 out, and then we just have the x there, right? X dx. Now, when I do the antiderivative of this, right, my power on this is a 1. So if I'm going to apply this rule, I would take, the n is 1, so I'd go 1 plus 1 up here, which is 2, right? I have x squared. And then I'd have divide by that same thing. You divide by that 2. So I add 1 to the power, and then I divide by that amount. And I put my plus c on there, and I have 3 times this, right? This 3 is out here, so 3 times that. So what do I have then? I've got 3 halves x squared plus c. Now, you can do a quick mental derivative and make sure that works, right? 2 times 3 halves is 3, and then I take 1 away from that, it'd be 3x to the first, right? That's what I have. And the derivative of any constant just disappears. Okay? Let's try another one. So if you have something like this, where you have if you have a monomial with your variable with an exponent in the denominator, move it up, make it a negative exponent, and work with your power rule. Okay? So we want to put it in a form that's easier to apply the power rule to. So I can call this x to the negative 3. Okay? Now when I do my power rule, I'm adding 1 to the negative 3, and then I'm going to divide by whatever that amount is. So if I add 1 to negative 3, I get negative 2. Okay? So that's going to be x to the negative 2 divided by 2. Right? So divided by, negative 2. We're dividing by negative 2 there. So whatever this power is, that's what I'm dividing by. Same thing here. I had x squared, I divided by 2. Here when I added 1 to that, I got negative 2. I need to divide by negative 2. And always put your plus c on the end. Okay? All right, and now let's probably simplify this a little bit, because this is not real great form to leave it in. So the negative exponent, probably move that down to the denominator again. And I would just think this is negative 1/2. And then I'd have x squared in the denominator plus c. Probably be the way you'd see that one. Okay. So the negative, I'm just going to pull that out in front of the fraction. The 2 stays in the denominator, but this x to the negative 2, we move it down, and now it's x squared, positive 2. Okay. Okay. Square roots or radicals, you want to change those to rational exponents so that, again, you want to have exponents so that you can use this power rule. Okay. So let's write this as x to the 1/2 power. And now work with some fractions, but so we have to add 1 plus 1/2, which is 1 1/2, or let's call it 3 halves, right? So I'm going to have x to the 1 1/2, or 3 halves power, and then I'm dividing by 3 halves, right? Now this is kind of ugly to do this, dividing by 3 halves, but when you divide by a fraction, it's equivalent to multiplying by its reciprocal. So instead of dividing by 3 over 2, I'm going to multiply by 2 over 3, so my coefficient is going to be 2/3. Hopefully that makes sense. If I'm dividing by 3 halves, it's the same as multiplying by 2/3, okay? So this is going to be 2/3 x to the 3 halves, and I'm going to put a plus c after it. Okay? And then again, do your mental math, just check that this derivative works out. If I multiply 2/3 times 3 halves, that's 1, and then I would take 1 away from 3 halves, which would leave me with 1/2. I just get x to the 1/2. 1x to the 1/2, that's what this is. Okay? Okay, part D. Now, there isn't like a product rule or a quotient rule. All we have really is this rule. So sometimes we have to, simplify first. So here what we're going to want to do is distribute, okay? And if I have x to the 1/3 out here, which is what that is, and then I'm distributing it through these parentheses, okay? Remember, this is an x to the first power. So when I multiply x to the 1/3 times x to the first, that's going to be x to the 4/3, right? 1 1/3 or 4/3, and minus 4x to the 1/3. So I'm distributing the x to the 1/3, right? Okay, now I still need to take my integral of this, okay? Excuse me. So applying the power rule to each one of these pieces. No, I'm not. I could write the integral of each of these pieces separately and show that this rule is being applied, but you can just do the antiderivative of each term that's in there as you go. So if I add 1 to 4/3, so think about that. It'd be 3/3 plus 4/3. That would be 7/3, right? It'd be x to the 7/3, and then I have to divide by 7/3, which means I'd be multiplying by 3/7. So it's 3/7 x to the 7/3, and then minus. Okay. Now this 4 is going to be multiplied in whatever I have with my coefficient. If I add 1 to the 1/3, that's 4/3. Be multiplying by its reciprocal, so dividing by 4/3 as well, so times 3/4, and this will be 4 times 3/4. I'll just write that 4 times 3/4 x to the 4/3. I hope you can follow that. So I'm adding 1 to 1/3, that's 4/3. And then I'm dividing by 4/3, which is equivalent to multiplying by 3/4. This 4 was from my coefficient that was there. Okay. Now I need to simplify all of this. I'd have a plus c. Don't forget at the end to put plus c when you're all done with your answer. Okay, so I got 3/7 x to the 7/3, and then this is going to simplify to just minus 3x to the 4/3 plus c. Again, let's do a quick check. 7/3 times 3/7 cancels, and then I take one away from this. That would be x to the 4/3, which is really what I had up here in this step, minus, and then when I multiply this, I'd have 4x to the 1/3, which is what I'd have here, and then derivative of a constant would disappear. So this would be the antiderivative of that expression. Okay? All right, and then for part E, what I've got here, I have this fraction. Like I said, there's really no quotient rule that we can use here. So what we want to do is we want to simplify it again beforehand, and we can simplify because there's just the one denominator, and this is why this is doable without. There are ways to do quotients where it's not set up in this form, but that's using some substitutions that we haven't quite seen yet. But what we can do with this, when there's just a single denominator like this, is we can rewrite this as x over the square root of x plus 1 over the square root of x. Now, that square root of x, I'm gonna rewrite that right now. That's x to the 1/2, right? We typically want to go to our rational exponents because that allows us to work with these exponents as numbers instead of the radicals. Okay, so if I have x to the first on top, and if I have x to the 1/2 on the bottom, so that's going to be x to the 1/2 plus x to the negative 1/2. And now I'm going to integrate this expression, okay? Because this, what I have here, is equivalent to what I have here. I just divided each one of those numerators by the denominator and then simplified. So now I'm able to use that power rule. So with this one, if I add 1 to 1/2, that's 1 1/2 or 3/2. So integral is going to be 2/3 x to the 3/2. So that would be my antiderivative of the first term. And then with the second term, since I have negative 1/2, if I add 1 to negative 1/2, I get 1/2. And if I divide by 1/2, that would be the same as multiplying by 2, right? So I have 2x to the 1/2 power. Okay, so let's check and see if that works. If I take 3/2 times 2/3, that cancels, and I take 1 away, so I get x to the 1/2. Yep, that's right. Multiply the 1/2 times the 2, that cancels. Take 1 away from 1/2, I get negative 1/2. So that works as well. Tack on your plus c, and you should be good. All right. Okay, part F, we've got, again, when we did derivatives, we could have used like a chain rule, power rule, and then use a chain rule here, but we don't have that here, so what we need to do is just expand this, so just FOIL this out. So we're going to have t to the 4th, and then when you FOIL this, you have first times second times 2, so that's going to be plus 2t squared plus 1. Okay, so I've got the integral of this expression. Variable of integration is t, so we put dt on there. Okay, so using the power rule here, if I add 1 to this power, I get t to the 5th, dividing by 5, so 1/5 t to the 5th plus, okay, and then here, if I add 1, 3, divide by 3, which is times 1/3, but then times the 2 that's there, so I'll have 2/3 t to the 3rd. So 3 times 2/3 is 2. Take 1 away from that 3. Okay, that gives me the answer I had there. And then with the constant, if I take the integral of the constant, that's just going to be 1t. So I just get t for that. And then I put a plus c at the end. Okay? So that is, what do we do there? 6 examples of some basic integration rules. Okay? Let's take a look here at our trig functions. I think we can do, let's go through example 2 on this video. Okay, so if you think about, if you had the derivatives somewhat memorized for the trig functions, the antiderivatives are, I think pretty intuitive somewhat. I want to draw this picture that I've drawn before. I might have to erase it, but I think I showed you guys this before. So in trig, we know that the cosine values are the x-axis values, so that's cosine. Over on the left, we're going to say negative cosine, and then the y-axis were the sine values, so I'm going to put sine of x up here and negative sine of x here, right? Now, if we were taking derivatives, we would move around this coordinate plane in a clockwise direction. So like if I'm going this way, sine of x is cosine of x. Sorry, the derivative of sine of x is cosine of x is what I meant to say. The derivative of cosine of x is negative sine of x. So going that direction, that is for derivatives, right? Now, if you rotate the other direction, if we go like this, if we go in a counterclockwise rotation, this is going to be the antiderivative. So if I were to take the antiderivative of cosine of x, I would get sine of x. If I take the antiderivative or the integral of sine of x, I get negative cosine of x. So I think this picture is helpful. It just kind of helps keep, in red I have the integrals. Okay. So let's see if we can fill this out. So I just said, so the cosine, the antiderivative of cosine of x, so if I were to start here, cosine, move this direction, that would be sine. Sine x, and then we put our plus c on there, right? And if you're like, oh, let's see now, if I do the derivative of sine, yeah, that's cosine, so that makes sense, right? Because they should undo each other. If I take the derivative of this side, that would give me what the integral was. Okay, and then with sine of x, here, if I do the integral, it's negative cosine of x, right? Negative cosine x plus c, technically. And if I take, if I take the derivative of cosine, I know that that's negative sine, and that cancels this negative and leaves you with just sine of x, okay? Now, if you remember some of these other ones, so cosecant squared, it was, the derivative of cotangent was negative cosecant squared, if you kind of remember some of those. So that means that the antiderivative of cosecant squared would be negative cotangent of x plus c, okay? And the co-functions, those were the ones that involved the negatives. That was kind of a trick for remembering which ones were negative. So the secant squared, that one was just going to be, if you took the derivative of tangent, then you got secant squared, so the antiderivative of secant squared would be tangent of x, and we put the plus c on there. The cosecant times cotangent, that was your that was cosecant, and again, since it's the cofunction, this is going to be negative cosecant x plus c. And then secant tangent, that was the secant one. If I do the derivative of secant, I get secant tangent. Okay, so that would be those functions right there. Okay, so let's just do these ones real quick. I'm going to pull this 2 out, and then I'm doing the antiderivative of sine of x dx. And so I have 2, and my antiderivative of sine of x is negative cosine of x, so it's going to be negative 2 cosine x plus c. That one. And the last one for this video anyway. So I have sine over cosine squared. Now, sometimes, you've all taken trig, and there's some, we know that there are some identities that a lot of times when they're in terms of sine and cosine, we can do some things and get some ratio identities. So here's what I would look at for this one. Because we don't have a quotient rule, let's just say, well, I have a sine on top, I got 2 cosines on the bottom, so if I had like cosine of x here, I know that that's tangent, and then I have another cosine, so I could kind of, think of it maybe like this, because that would be equivalent to right here, because I'd have cosine squared. Now sine over cosine here is going to be tangent of x, and then 1 over cosine would be secant, okay? And so that gives you this product of tangent secant, or secant tangent, same thing as what we have here, and the antiderivative of that, my integral sign on there, the antiderivative of that is, we know that that's secant, okay? So the answer to this is just going to be secant x plus c. Okay, so that's all we're going to cover for this video, and we'll continue on in the next one.